Hello everybody, this is Mr. Johnson, and this video is about how to graph logarithms. We've been learning a little bit about exponential functions. These are related to those, but they're slightly different. In fact, a logarithm function here, it's the inverse of an exponential function. Earlier this semester, we talked about inverses when we were doing roots. Roots are sometimes the inverses of exponents. And when we look at their graphs, the graphs are flipped versions of each other. They're mirror images. And if you remember, we drew in like a dashed line, and everything that was over on that side of the graph got flipped to be over on this side of the graph. So it makes kind of a nice little picture there where both sides are symmetrical. If we look at this first particular exponential graph, f of x equals 3 to the x power, we're starting and we're centered here at the origin. That's where we'd put our little star. Now exponentials, if you recall, have a horizontal asymptote. So I need to put that in. And it looks like it just covers up the x-axis. We can't hardly see it, but we can't pass that line. Now if I'm looking back at the equation, technically 3 is hooked to the exponent, and there is an initial value of 1. So if I zoom in here, there's a 1 in front of that 3. That means my initial jump is going to be up here at 1. Now the 3 is still pretty important. The 3 tells us the pattern that goes with this. Since it's a 3, we know that we should be tripling. So this first initial distance of 1 will get tripled and become 3. And this is as I'm going to the right. I always start by going in that direction. And then if I triple 3, I get 9. If I triple 9, I get 27, and so on and so forth. It just keeps getting bigger and bigger. So let's go ahead and let's mark those distances. Remember, it's always how far you jump from the asymptote. So 1, 2, 3 boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes. 27, too big. I can't jump that high, at least not on this graph. If I'm going the other direction, I need to be dividing. So if I go to the right, I multiply. If I go to the left, I am basically dividing by 3. So 1 divided by 3 is going to be 1/3. 0.333333 forever. If I go and divide that by 3, I get 1/9, which is 0.111111 forever. And it keeps getting smaller and smaller and smaller, approaching that asymptote. Now recall that we will not touch the asymptote, we just get close to it. And it kind of looks like we do, but if we zoomed in, there'd be a little space there. So the domain of the range, the x values here that we use, we go left forever, this direction, and we will continue outwards in the right-hand direction forever as well. So that is double R. You could also write negative infinity to positive infinity. That's the same idea. The range, or the y values, I don't go up and down forever because there's this asymptote in the way. So I'm stopped by the asymptote. The only place that I actually graph it is right up here. So if I'm going to say that for my range, I need to go from 0 to infinity. Now I can't put a bracket on 0 because I can't touch the asymptote. If I equal out 0, I would have a bracket, which I can't equal 0. Another way you could write that would be y is greater than 0. It's not greater than or equal, it is just greater. So how does this compare to maybe the inverse, which is really what we're going to focus on? We don't even have the equation over here, but you can see f inverse has that little negative sign up there. That tells me to say the word inverse. So we write the equation as log, literally the word log. Now, because this graph over here had a 3 as its base, logarithms are kind of weird because they also have a base, but it's down there at the tail end of the G. So this is log base 3. Okay, so that is the inverse of an exponential with a base of 3. Now I still need an x. I can't just have log 3. That doesn't really do anything. So I put parentheses here and I put a little x inside of the parentheses. Notice the x is kind of big. It's a normal size, whereas for exponentials, the x is small. It's teeny tiny because it's up in the exponent spot. So positioning is important. So how do we graph this inverse, which is the log function? Well, we actually start in the same spot. So we're going to put our star right here on the origin. But because this is the inverse, things get flipped around. The x's goes to the y's go to the x's. So my horizontal asymptote is now a vertical asymptote. It's going in the opposite direction. Now, I like to remember this because log has the letter L at the very beginning. And which direction does the letter L go? It goes up and down. So it's a nifty little way to remember that logarithms will have a vertical asymptote. That's always the first thing you start with. Now, for ours, we are going to be having our first point be 1 away from that central point. There are things that you can do to stretch it and make it go out further to the right, or you could even flip it and make it start on the left, but we won't be doing those things. Those are pre-calculus ideas. So 1 away from my star, and notice how I went 1 away from the asymptote to the right. If I take that and I look at my base, the base tells me what pattern to multiply by. So since it's a 3, I am tripling. Now, which direction do I go? Do I triple and go like down here? Or do I triple and then go up here? Well, the default is going upwards, okay? You're always kind of going from the bottom to the top. So I will go 1, 2, 3 boxes away from the asymptote. So I was 1 away, I've tripled that distance. Now I need to triple that distance to make 9. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes away from the asymptote. So again, I'm always jumping away and away and away. So if I'm multiplying as I go up, that means I need to divide when I go this direction. So if I take and divide 1 by 3, that's 1/3, 0.333 forever. 1/3 divided by 3 is 1/9. And notice how I'm writing these distances off to the side, because it's very hard for me to tell what 1/3 looks like versus 1/9 or 1/2. And so if you don't have these numbers, I will have to count you off slightly because I don't know exactly where that dot is situated. This is your work for graphing exponentials and logs. You have to have that. So when you get a couple points above and below, go ahead and draw your graph in there. Draw that curve in. All right, and again, I don't care if it's kind of messy. What I'm looking for is those points. So the domain, the x values. Remember, inverses, they kind of switch this around. So if I look, it's not going to be the same thing as the domain over here for my exponentials. In fact, it's going to be the range of my exponentials. Does that make sense? Well, if we look at the x values, going this direction, there's a fence. There's that asymptote, which means I can't cross right here. I only can be on that side, which means I'm limited from 0 all the way out to infinity. I can also not touch 0. I can't touch that asymptote. I get really close down here at the bottom of my graph, but I never actually will equal 0. So let's talk about the range, the y values. This goes down forever, and it continues up forever, not very fast, but it will keep going up. It's not limited by another asymptote. So that means I go from negative infinity to positive infinity. Now we know that's double R. If I compare that with the domain back here, they match up. So if you recall inverses, as I zoom out, the domain of one will map to the range of the other. The range of one will map to the domain of the other. And you can see they match up pretty well. In fact, I could, for the domain of the logarithm, say, hey, x is greater than 0. So it even has that thing in common. So let's go ahead and let's compare and contrast some of these things. What's similar and what is different? So if I'm looking at these, I'm going to do a little cheat here. They have similar patterns. Oops. So you're multiplying as you go in one direction and dividing in the other direction. You're jumping away from the asymptote. Those are similar patterns. Both have asymptotes, but one difference is that they go in opposite directions. Exponentials go horizontal with their asymptote. Logarithms, because remember the letter L They go vertical with their asymptote. So those are a few things that you need to keep in mind, okay? You could also talk about which direction the graph is going based on that asymptote. There are all sorts of comparisons that you can make here. But if you have this idea in mind, you will do fine graphing exponentials and logs. Let's go ahead and let's look at the next side. Let's compare and contrast with a little bit of a table. So if I'm looking here at f of x, we learned that to be the exponential graph. All right, so for example, in the previous problem, it was just 3 to the x power. Now the inverse of that would be called a logarithm. Why he called it that, I have no clue. But that literally looks like this, log 3 with a little x inside. Now we can talk about which axis they cross. So we're talking specifically about the graph. So the graph will always cross, for an exponential, the y-axis. And that's because it goes left and right forever, so you have to cross the y-axis. Now, it doesn't mean that you can't cross both, so I will put both in parentheses because depending on where you move it, you can also cross the x-axis. For logarithms, that's a little bit different. You are always going to cross the x-axis, but again, if you move things in a certain direction, you can cross both of them. You are not limited to just the x-axis. It just depends on where you're at. But you will always, always, always cross the x-axis. Now, what happens if b, or the base, is bigger than 1? Well, that's pretty easy for exponentials. You are just dealing with growth. For logarithms, it's kind of the same thing. It's growth, but it's not growth up and down. It's growth in the outwards direction. For the b values, exponentials, that just makes it decay. Remember, small values make it smaller and smaller and smaller and smaller. Logarithms, that does something similar, so you can put decay in parentheses, but we actually won't be doing any of those. All right, it flips the graph, and it looks kind of funny. If you're interested in this and you really understand what we're doing, I would encourage you to try this on maybe Desmos or another graphing calculator of some sort. It's kind of cool. So the asymptote, specifically the equation of the asymptote. So when I look at exponentials, that asymptote goes like this, and that will be y equals a number. If I look at logarithms, their asymptote is vertical, and I write the equation of a vertical line like x equals a number. And we'll talk more about that here in a minute. Domain and range. For exponentials, it's all reals. Since they are inverses, I know I can flip-flop them, and the range of a logarithm is all reals. We just saw that. This even works if we're going in the other direction. So the range for an exponential is going to be limited by the asymptote. I will abbreviate here for asymptote because it's kind of a long word. And then the domain for logarithms, that's also limited by the asymptote. So it changes based on the numbers in our problem, but it will always be limited. So let's talk about what happens if b gets bigger. If b gets bigger for an exponential, we grow up faster. But if b gets bigger for a logarithm, we are not growing up, we're growing out. And that's really important. We grow out faster. So there are two types of logarithms that are considered to be special. They get their own names, and they look slightly different with their equation. So the first one, it happens so often they called it the common logarithm. They got tired of writing it every single time. Kind of like how square roots, they dropped the little 2 out there as the index because they just happened so often that people got lazy. So the common logarithm has a base of 10. So that means multiplying by 10, dividing by 10. Scientific notation kind of goes along with this. So when we write this, we are only going to use the word log. There's an invisible teeny tiny 10 down here, but we can never see it. Your calculator should have a button on there that just says log. That's log base 10. That's a common log. So just keep in mind, you can't see that 10. It's like invisible. That's why you can hardly see it. So if I go back down to the next part, there is another log called the natural log. It has a base that we already have talked about. It has the base of e, which, remember, just the number 2.7, and it goes on forever. It's painted out in the hallway. Many times, the natural log is written as ln. All right? So keep in mind, there is an x after all of these. So log of x, ln of x. Now, ln, since the fellow who made these up, I believe, was French, it stood in his mind for log naturel. So that's why you have L and N. Or you could think about that just in your head as log with the base of E. All right? And again, that's not how we will write it. We will write it mostly as ln of x, but it means the same thing. All right? It just shows up so often that they didn't want to write log because they were lazy. Let's talk about some of the equations and the numbers in the equations and what they do. So our typical equation for logarithms will have the word log in it. It will have our base. This base is super important. It tells us the pattern. It tells us what we are multiplying by. And usually, this will be a number bigger than 1. We won't do little fractions. We won't do negatives down there. That's weird stuff. Okay. In fact, negatives down in the base kind of break logarithms, like negative for bases of exponents broke exponents. So if we look inside a negative h here, that moves us left or right. And then at the end, plus k, that's up or down. The movements that we've been seeing had just occurred The movements that we've been seeing are the same movements from the very beginning of the year, and that's really important. There is consistency in math. So let's go ahead and let's graph some of these. These examples will go fairly quick, and there's a series of steps to do them. So 14, y equals the log base 7 of x. Notice how I read that equation out. This is not moving left or right. In fact, the only thing it tells us right here is 7 means we're multiplying by 7. So I am centered right there at the origin. Since it's a logarithm, which direction does my asymptote go? It's going to go up and down, just like the letter L. So draw that in there. Again, you can hardly see it because it's on the y-axis. And then for logarithms, we are just going to start next to the star, 1 box away. There are other things that you can do to stretch it. Again, we are not going to do those. So your default here is just 1 box. It will always be 1 box for our class. Now after that, I have to go ahead and multiply by the base. So 1 times 7 is 7. 7 times 7 is 49. And then you take 49 times 7 and you get a really big number. So let's go ahead and let's jump those distances. And again, this is how far you count away from the asymptote. So I was 1 box. Now I'm 1, 2, 3, 4, 5, 6, 7 away. I'd be 49 away, which that's way off the graph. Now, that was multiplying. I am multiplying as I go up, but I need to divide as I go down. So dividing by 7, that makes 1/7. Dividing by 7 again, that makes 1/49. You'll notice there are patterns between the two sides, multiplying and dividing by 7. If I go 1/7, that's a teeny tiny amount. If I go 1/49, which is the next box down, that's extremely small. It's like 0.02 almost. It's like 2 pennies out of $1. So connect all those. Again, it looks like we're on the asymptote, but there's a teeny tiny space there. So if I look at 15, g of x, it doesn't appear like there's any base down there at all. It does not mean 0. In fact, this is a common log. It means there's a base of 10. So this is a special one. It's a common logarithm. So I'm multiplying by 10 every single time. Multiplying by 10 is pretty easy. Now we also have another number, plus 1. Well, that just moves us left 1. So when I am looking for the center of my graph, where I put my star, it's just left 1. Since it's a logarithm, we have a vertical asymptote. So I'm going to go draw that in right here, and we cannot cross that asymptote. Our logarithms are always going to be on the right-hand side over here. So we will not flip them. We'll never go over on the left. Don't do that. My first dot is always 1 away from the star. If you go to pre-calculus, you'll learn how to put those dots in different spots. Ooh, that rhymed. So 1 gets multiplied by 10. 10 gets multiplied by 10. 100 gets multiplied by 10, and it keeps on getting bigger and bigger and bigger. Again, I need those numbers so I can see if you understand the pattern. If I'm going down the opposite direction, I divide by 10. So I get 0.1, I get 0.01, I get 0.001, and then it keeps getting smaller and smaller and smaller, 0.0001. Those are all small distances, but they're never going to equal 0 because I can never touch the asymptote. It just gets really close. So if we mark those, so 1 away, now I need to go 10 away. Notice I'm starting at my asymptote. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lands me here at 9 because I had 1 box to the left of the axis. 0.1 is really close. 0.01 is super close. 0.0001 or whatever, that's like you can hardly tell the difference between that and the asymptote. Draw your curve in. Try not to be blatant about where you are on your graph, and that's all you have to do. Fairly simple and straightforward. So let's look at 16. 16 has ln. Oh boy, what in the world does that mean? You should be thinking in your mind that's basically log e, good old log e. Log e of x plus 3. Well, e is just 2.7. So we're multiplying by 2.7 and dividing by 2.7. That shouldn't be terribly hard. We just need a calculator. Now, where do I move? No, the plus 3 tells me I need to move up 3. So up 1, 2, 3, I put my star right there. Logarithms have vertical asymptotes, so I draw that in. Can't cross that. And then my first dot is 1 away. Now 1 multiplied by 2.7 is 2.7. 2.7 multiplied by 2.7 is 7.29. 7.29 multiplied by 2.7 is 19.63. So 68. Okay, if you have a calculator, this is all you have to do. 1 times 2.7. There's your answer. Times 2.7. There's your next answer. Times 2.7. There's your next answer. Times 2.7. There's your next answer. When I was a little kid, I was kind of a nerd, and I would sit in the kitchen with my mother and play on a little calculator. And all I would do is I'd hit times 2, times 2, times 2, times 2. It's the same idea, and I would try to see how big you could make those numbers. I'm sure some of you guys probably have tried that in my class because you just get bored of listening to me talk all the time. Well, that's good because you're kind of learning some math facts there. So if I divide by 2.7, I'm just going backwards. I can get all the way back down, as long as I don't screw up with the numbers, to 1, where I started. So if I continue and I divide by 2.7, I get 0.37. If I go ahead and do the same thing, divide by 2.7, I get 0.137. Those numbers will continue to get smaller and smaller and smaller, closer and closer to the asymptote. So 0.137 is really close. 0.37, kind of in the middle. 1, 2.7 is out here close to 3. 7.29 is out here, a little bit past 7. And then 19, the next space, would be too far off the graph there. As long as you're getting close to your dots and getting close to your asymptote, I'm a pretty happy guy. So don't be concerned when you have a natural log. It just means 2.7, and 2.7 is not a nasty number. If you are peeking ahead, 17 is actually the same thing. It has log and then 2.7, x plus 1, and then minus 4. Again, that's just e. So you got the lodge there, L-O-G-E, classic. Anyway, this goes left 1, and it goes down 4. I'm hoping that you have nightmares about those directions because you've talked about them every single day of your entire life in Algebra 2. Yippee. So, Left 1, down 4, puts me right there. That's where my star goes. Let me zoom in here. Since it's a logarithm, put in that vertical asymptote. First dot is 1 away. Now, because it's a natural log, I just multiply by 2.7. So I'm going to use some of the same numbers as the last problem. 2.7 away, right there. 2.7 times 2.7, 7.29. All the way out here. Whoops. Now, notice, I actually made a mistake. These are all on the same spot, the same plane. So I need to adjust it, and I need to always be going up a box, up a box, up a box. If you are on the same level, that is bad. That means its inverse would not be a function, which isn't good. Over here, if I'm dividing as I go this direction, 1 divided by 2.7 is 0.37. It's not kind of in the middle, and then I have 0.137, really close to the asymptote. Connect those dots, go this direction, and you are good to go. If we go ahead and look at question number 18, we can see that it's a log with a base of 4. That's going to be important because that means we are quadrupling. We're multiplying by 4 as we move up. So 4 is our pattern. Sorry for the sloppy handwriting. Minus 3 inside with x does the same thing. It's going to move us right 3. It's a translation. It's a shift, and then the plus 4 at the end, that moves us up 4. So that's exactly where our start goes. Right 3, up 1, 2, 3, 4, put a star there. Since it's a logarithm, vertical asymptote. That means we can't go past it in the horizontal direction. It limits us there. That means it's going to limit our domain. Logarithms will always be 1 point away from our star. Then I multiply by 4 since that's my pattern. So 4, 16, 64 would be pretty far away. I probably won't ever get that. So 1 box away, 1, 2, 3, 4 boxes away from the asymptote, and then 16 obviously wouldn't fit. Going in the opposite direction, I need to divide. So that's 1/4, and then 1/16, and then 1/64. You notice there's patterns up and down with some of these numbers. 1/4 being 0.25, 1/16 being even smaller than that, even smaller, and even smaller. So you can go ahead, draw your curve, making sure you don't cross the asymptote, that you're following exactly along it, even though there's a little space there. I understand what you mean. So domain and range. The x values, it does not go left and right forever. It's limited by the asymptote. So that would be from 3 to infinity. Parentheses on both of those because you can't touch 3. 3 is the asymptote. You could also say this, x is greater than 3. For the range, the y values, that would be down forever and up forever. Double R. Doesn't matter to me which one of those methods you write your answer in. Both are perfectly fine. Question number 19, h of x. This is the log, but there's not a number down below. So when you see that, you should know that it's a 10. It's an invisible 10 because it's a common log. So we are moving right 2, and we are moving down 3. So right 2, down 3 puts my central starting point right there. Logarithms have vertical asymptotes. You can almost think of it kind of like a tree, growing up and growing down. And then my starting point is always 1 away. So logarithms, I think, personally, are easier than exponentials because you don't have to worry about that initial value. So 1 away, now we multiply by 10. Then we multiply that by 10 to get 100. 100 times 10 is 1,000. 1,000 times 10 is 10,000. It just keeps getting bigger and bigger and bigger. So really the only one we can get in is 10. That'd be somewhere out there. 10 spaces away from the asymptote. If I'm going in the opposite direction, I'm dividing by 10, which gives me 0.1, 0.01, 0.001, and you see there's a pattern. I just keep adding zeros in there. Dividing by 10 has a habit of moving the decimal place. That's kind of where scientific notation comes from. So we draw our curve in, trying not to go past the asymptote. I'm just looking for those points, and I'm looking for these distances. If you don't have the distances, I can't give you full credit because I don't know if that's 1/10 or 2/10, if that's a fifth or a tenth. And so I have to know that you're doing the math correctly there. And the math goes with the base. The base is the pattern. The domain, the x values that we use, go from 2 to infinity. X's would be greater than 2. I cannot put equal. That would mean I'd stand on the asymptote. That's bad. The range and the y values go everywhere, from negative infinity to positive infinity. Double R is how we represent that. All real numbers. And our last set of questions, 20, 21, and 22. We're trying to write an equation for these logarithms. If you remember the exponential equations, we could have a ton of different exponential equations. With logarithms, there's really only one, and that's because we're limited to where the space is 1 away from the asymptote. So that means right there and right there for question 21. So we're kind of limited. We can't move up and down on the asymptote when we start. So let's go ahead for number 20 and put our star in. That's when our distance is 1. And we have to see what pattern we're doing here. My next distance, if I count right there, is 2. Let's see, 1 to get to 2, that's multiplying by 2 as I go up. So this one, if I multiply by 2, I should be 4. If I count 1, 2, 3, 4, I do happen to have a dot right there. So that's really important that we double check. If I'm going downwards, I'm just dividing by that amount. So divide by 2, this should be 0.5, which it looks like that's where that dot is located. Then 0.25, and then 0.125. Oops. Smaller and smaller and smaller. So that means I'm multiplying by 2. In order to get to the star, I have to move left 3. So let's talk about how to write the equation. First off, y equals in log. The base is going to be 2 since I was multiplying by 2. That's the pattern. Inside of the parentheses, I have x, and since I moved left 3 to get to that starting point, it must be plus 3. That would move me left 3. The star didn't move up or down, so that means there's nothing here at the end. No vertical translations. So that's my equation. That would be the one equation that we know how to make to get this shape for our logarithm. Again, reinforcing domain and range. The x values go from negative 3 to infinity. Or you could say x is greater than negative 3. And then the range, the y values, would be, sorry about that, double R, from negative infinity to positive infinity. Not bad. Question 21 is exactly the same, just a different shaped graph. So we find the spot where we're 1 away, which happens to be right there. So we have a movement of going down 1. Now we have to figure out the pattern. This is 1. Our next would be 1, 2, 3, 4, 5 away to get to that dot. So 1 to 5, my next one would be 25 because I'm multiplying by 5. That means 1 divided by 5 is 0.2, which looks to be about that distance right down here. It's a small distance. So when I write it, y equals, or you could even use a fancy notation, f of x equals, nothing in front. We aren't flipping them or anything like that, but I do need the word log. Since I'm multiplying by 5, that means I need to have a log base 5. Inside, I don't have any left or right movement, so it's just x by itself, and at the end, minus 1 since it moved down 1 right there. Domain, again, from 0 to infinity. I'm only over in this part of the graph, so you could say x is greater than 0. And the range from negative infinity to positive infinity, or you could say double R, all real numbers. So the very last question on your notes, describe the differences between exponential and logarithmic functions. I will leave that up to you. Realize that they're inverses, so they're kind of like opposites of each other, and so they have different patterns slightly, even though their patterns are similar. There are differences in which direction you go, and things like that. Domain and range would also be swapped there. That would be a difference. So if you have any questions, feel free to email me. You can watch this video as many times as it takes, especially if you miss a day. That is very, very helpful, or if you need to go back and practice and look at one of the problems again. So I hope to be back soon, and I miss you guys, and we'll talk to you later. Bye.